All right, let's look at this. So this is some stuff we talked about yesterday, right? So what did we say about, kind of at the end of the day yesterday, we talked about some properties and radicals, how we could write a radical as an exponent. So for example, if we had the cube root of 11, how could I write that? 11 to the 1/3, good, right? Whatever is the number that goes with the radical, the index of the radical, that's what goes on the bottom of the fraction, 1 divided by that, right? Okay, so what if we had, real quick, what if we had the square root of 17? That's what? 17 to the 1/2, whoops, half, because there's an invisible 2 up there. It's a square root. When we square things, that's a second power. So that's the number that goes on the radical, right? That's the index. Okay, then what about something like this? What if we've got the square root of 3 to the 8th? So we just said that the number that goes there is a 2, right? So whatever's inside the radical, phones should all be completely away, please. You would be absolutely insane not to be paying attention to this. I mean, there's so much good potentially at stake for you on this test. It would be I think it would be a horrible decision not to try to take advantage of that. So what power are we taking everything inside to? Whatever's inside we're taking to 1/2, right? Because we got a square root. And what's inside is a 3 to the 8th. Well, look what we've got then. We've got a power to a power. What's our rule for a power to a power? Yeah, we multiply. Good. Take a power to a power, we multiply the exponent. So we get 8 times 1/2, which is 3 to the 4th, right? Okay? No big deal. Now, if you have the Desmos calculator available, a lot of this stuff becomes extremely simple. So what we would do here then, if we have the Desmos calculator, I would just go up here, first of all, anything you can do on a calculator, Desmos will do it better. So if I want to know what the decimal value of that original square root is, all I've got to do is type in square root. So if I go down, there's the square root button, right? Okay, I can either hit that or there's a shortcut. If you just type in squirt, S-Q-R-T, it automatically makes a square root bracket for you, right? So square root of 3 to the 8th is 81, right? It tells me what the value is. Then all I would have to do from that point is just try each of those and see which one's going to give me the right answer. Which one's going to give me 81. So if I do 3 to the 1/4, no dice, right? So we'll go ahead and replace the 1/4 with a 3. 3 cubed is 27. Nope. 3 to the 4th is 81. We got it, right? So if you can use Desmos, it's easy to check or do the problem that way. All right, next. Okay, what about something like this? We've done a lot of this stuff. A lot of this stuff. This is pretty new. Should be pretty fresh in your mind. What do we do when we're adding up a bunch of quantities like this? Add like terms, right? So we'll just distribute and add like terms. Well, this first quantity up here, what's out in front of the quantity? 1. So I don't need to change anything. I can just get rid of the parentheses. Distributing 1 is the same as just leaving everything the way it is. So sure. It is, bro. Something's going on. He's following us. No, I don't think so.
Jeez.
Okay, I'm going to ask one more time. All phones should be put away or I'm going to go ahead and collect them. Send them down to the office. Okay, we're back. All right, so we were saying then this first set of, this first quantity, we don't have to change anything. What about the second one? What are we distributing on the second one? 1. Don't need to do anything, right? So that just stays the same. Okay, what about the last one? -1. So I've got to distribute a -1. What's that do to all the signs? Flips them. So I'm going to get minus x squared minus 3y squared minus x, and then all I've got to do is just add like terms. So let's look at the x squareds. I've got 3x squared plus 2x squared is how many? 5x squared minus x squared? 4x squared. Okay, and those are taken care of. Okay, what about the y's? I get 2y squared plus y squared, 3y squared minus 3y squared, 0. So those just completely cancel. Okay, and then finally I get -3x minus 2x, -5x minus x. Okay, there we go. So that's the answer, right? Now, how can we check this one? What's our way to check to see if things are equivalent? What do we do? Put in random numbers, right, for x and y. So I could do that if I don't have access to a fancy calculator. I could pick easy numbers like 1 for x, 2 for y or something, right? Plug it into the original, plug them in here, and I should get the same thing. There is a tricky way to do this on Desmos. Right, you don't have a calculator or a phone there, do you? Okay. So on Desmos, here's what I could do then. Check this out. This is pretty tricky. So normally, I think I showed you the trick yesterday where you can do f of x equals something and then just plug a value in for x and for g of x and things, right? Okay, now look at this first one up here. Here, you guys read this. Chris, read this off to me slowly. So what's the first quantity? 3x squared. Okay. Keep going. 2y squared.
3x plus 2x squared.
Okay, so then I got plus the quantity, right? 2x squared. Okay.
Plus y squared minus 2x. And then you got negative x squared plus 3y squared plus x.
X squared minus 3y squared? Plus.
That's a big one. Plus x.
Plus x, okay. Okay, so on that one now, I can't just call this f of x, right? Because there are x's and y's. So what I have to do instead, if I want to be able to plug numbers in, watch this. This is a great trick. You'll be the only students in America that know this trick in Algebra 2. So you go f of, and then what I'm going to do is I'm going to put in an x, comma, y equals. Okay, what's that mean? It's just if I have more than one variable to plug stuff in for, I just put a comma between them, right? So now if I pick some random numbers here, I could do something like I could take f of, they don't even have to be integers, they could be decimals, like 1.2 for x and 3.5 for y. It tells me what the answer is right down there when I plug that stuff in. So then all I've got to do now is take my simple answer here in purple, and I could just call it f of x because there are no y's, but I could even call it xy to keep everything the same, equals 4x squared. Oh, I can't call it f though. Whoops. I might have to call it like g, right? I already defined f, so we'll call it g. So 4x squared minus 6x. So I got these two functions now. All I've got to do is evaluate the function g at the same place, right? So I'm going to do g of, and I'll just copy that. So g of the same numbers, what do I get?
Same thing.
Same thing. So what's that mean? I did it right. They're equivalent, right? Okay. Okay, a lot of stuff like this. These ought to be really easy for you guys. We've done a lot of algebra, you know, order of operations stuff. So what we're supposed to do here, Emily's solving the equation, this equation right here. So that's, she just copied it down in step 1. click on the first step in which Emily made an error, and then click on the correct solution. Obviously, I can't do all, I mean, we're not in the test, so I can't just click, but I'll circle them. So let's go through these. Can you point out where's the first place where she made a mistake? Yeah, what'd she do? Yeah, here's the mistake, right? 28 plus 2 should be 30, right? And she got 26. So there's the step where she made a mistake, right? So what's the right answer? Well, let's just keep going with this. If that's a 30, what's going to happen next? So she subtracted 2x from both sides to get 2x on the right. She subtracted 26. She should have subtracted 30, right? So if she subtracts 30 from both sides, what's she going to get over here? Not negative 8, negative 12. And then if I divide by 2, I get x equals, there it is, right? Okay, no big deal. How could I make sure I got it right? Plug it in, right? Just plug it into the original equation and make sure it works. If I plug negative 6 in, I'm going to get 2 times 3 is 6 on this side. How about here? Negative 6 plus 7 is what? 1. 1 times 4 plus 2? No. Good addition. 6 equals 6. So we got it, right? Okay, how about this? Same thing.
Same thing.
Same kind of thing. Okay, so where's the mistake here? Okay, first step. This should be when she distributes the negative 4, that should be a positive 4y, shouldn't it? Right? So then if that's a positive, everything else is fine. Negative 24 plus 4 is negative 20. If I add the 20 to this side, I do get 16. Only that should be a positive 4y. So what's my answer? Positive 4. Okay? No biggie. Okay, what about these? We did a lot of this stuff earlier in the year. When we're solving inequalities, it's just like equations, but there's one difference. What do I have to be careful about? JJ, what is it? If I divide or multiply by a negative, I have to do what? Flip the inequality. Good. So on this one, we're going to divide each side. To isolate the end, I divide each side by negative 6. Right? But when I divide by a negative, I got to flip that around. Right? So I'm going to end up getting n on the left. I'm going to get negative 12 over negative 6 is 2 on the right, but I got to flip the inequality, so that's my solution. Right? Okay? So here's the answer. Okay? In Desmos, you can do this whole thing. Now here's another hint for Desmos that makes Desmos work a lot better. It allows you to do more stuff with it. So in Desmos, just like on our graphing calculators, what's the variable, like if we're going to graph something, what variables does Desmos assume we're using? X and Y, right? So when we solve an equation like this with n's in it, all we'd have to do is go back to the original thing, and instead of using n's, let's just graph it with x's. So if I go down here on Desmos, and I do this, if I do negative 6x is less than negative 12, look what it does. So it graphs this whole region over here. What are the x values graphed in this region? Because remember, we used x instead of n. So what does the dashed line mean? Okay, nothing on the line. It's just a boundary, right? So if we look at the part of this that's on, the x-axis, that means I have an open circle there, right? And we're just graphing everything to the right. Well, what's that saying? That's at 2. So we're picking all the values of x, or in our case, n, that are greater than 2. So it works, doesn't it? Okay, that's the same thing we got algebraically. Okay? Okay, same kind of thing. Click on the region of the graph that contains the solution set of the system of inequalities. So we talked about linear inequalities that use both x's and y's earlier also. Right? Remember what we said with these. When you have, let's just take the top one first. So if we take this top guy up here where we have y, whoops, we have no, it's working. Y is less than or equal to negative 1/2 x plus 3. Think what that is. It's giving us a boundary line. You know, mx plus b is the boundary line, but the inequality is telling us which part to shade, right? Because we're going to shade a whole half plane on this one. So what's the slope of the boundary line? Negative 1/2. What's the y-intercept of the boundary line? 3. Okay. So we've got 3 is the y-intercept. The slope is negative 1/2. So we'll rise by negative 1 and run by 2. And so because I'm including the equal sign in the inequality, is it going to be dashed or solid? It's going to be solid. Right? No, do you see why it's dashed if you don't include the equal sign? Because that means it's just a boundary.
Takes more ink.
Takes more ink, that's right. Now you remember that, that's good. Takes more ink. So there's the boundary line. Now we got to figure out which side are we going to shade, right? So there's 2 ways to do this. There's a shortcut way. If it's written, if y is by itself, it's really simple. Y is the vertical variable, right? So just think about this. If we're going to shade all the values of y that are less than or equal to the line, am I going to shade above or below? Below. Vertically, I want to pick lesser values, which means down, right? So I'm just going to shade everything on that side, right? Okay, there's another way to think about this also. You could also, this will always work, you could also always test the point. Let's pick the easiest point we can and see if it makes this true. If it makes this inequality true, then that's the side we have to shade because it's a solution. Well, what's the easiest one to pick always? 0, 0, as long as it's not on the boundary line, which it's not. So if we were to test that point, if I were to plug in 0 for y and 0 for x, what would I get? 0 is less than or equal to negative 1/2 times 0 plus 3. Well, that's just 3, right? Is that true?
Yes.
That is true, so I would include the side with the test point, right? Either way, we're shading down, okay? What about the other one? The other one looks like y is greater than or equal to 2x minus 2. So am I going to include the boundary line?
No.
Yes.
Yes. Right? Why am I including the boundary line? Well, but I want you to answer. You were in the room when we talked about this. So why is it? What about this inequality means we include the boundary line?
Equal.
Equal. There you go. Okay? So what's the y-intercept of the boundary line? 2?
Negative.
Negative 2. Good. What's the slope? 2. So 2 over 1. So we're going to start at negative 2. We're going to rise by 2 and run by 1, right? So here's my blue boundary line. Now we can take the shortcut because y is by itself. Y is greater than or equal to the boundary line. Which way am I shading? Up. Yeah, I'm going to go up, right? In this case, up also means, you know, to the left, I guess, right? So we're shading everything up there, right? If we were to pick the test point and plug in 0, 0, would that work also? If I plug 0 in for y and 0 in for x, I'd get 0 is greater than or equal to negative 2. True, right? So we would include the side that has 0, 0, has that point. Okay, so then what do you think then? If we're going to click on the region of the graph that contains the solution set of the system of linear inequalities, where's the solution of everything together of the system? Where they're both shaded. Yeah, it's going to be the double shaded part, right? Because remember, a system has to make both parts, every part of the system has to be true also. So we would only pick this part in there, right, where they're both shaded. Okay? So how do you do that on Desmos? I mean, if you can use Desmos on this question, it becomes really simple. It does all this stuff for you. You know, what's weird to me is that it's showing up on every problem on the practice test and it didn't used to, like last year. So it makes me wonder if it really is included. I don't know. We'll see. So here's my first recommendation. I would definitely recommend, do you know how to change the colors on Desmos?
Yeah.
Okay, I'm going to show you. I would recommend you use red and blue because those are really easy ones to see the overlap. So we're going to go y is less than or equal to. Well, I can find that down here on the keyboard. There's my less than or equal to, right? I can also take a shortcut. If I just type less than followed by equals, it knows to make it less than or equal to. So less than or equal to negative 1/2 x plus 3. So there's the first one. Here's how I change colors. If you go to the gear and we click on the circle, I can change it to any color I want. Okay. You like the orange?
I like the green one.
You like the green one? Well, tough. I'm going red. Okay, so there's the red. Now we'll go down and do the blue one. We'll do y is greater than equal to, so greater than or equal to 2x plus 2. And what do you notice? Okay, so you see that there's the shaded region right there, the double shaded region, right? Okay? All right. Yeah. Desmos would really help. Okay, this is super easy. We've talked about this stuff, I mean, so many times. So now let's remember the connection here. It says choose the ordered pair that is a solution to the equation represented by the graph. Think what a graph means. If I've got some equation represented by a graph, the solutions to the equation are just the points on the graph, right? There are an infinite number of points on that graph. Infinite number of points on that graph, and each point on that, I mean, really, it's like little beads strung along a wire, and there's just an infinite number of them jammed in there. The convenient ones are the ones that fall, like here would be a convenient one. That one's at 0, 2. This one is at 6, 6, right? This one is at negative 6, 2. So those are convenient ones because they're integer coordinates, but there's one right there also. Who knows what that decimal values are for those x and y values? They're all there, right? So if we're trying to choose the ordered pair that's a solution, it's got to be the point that's on the function, that's on the graph. So which one is it? Negative 3, 0. Or 0, negative 3, right? Not negative 3, 0. It's got to be the x value is 0 and the y value, oops, hang on. Oh, negative 3, 0. No, you're right. You're right. My mistake.
Because it's on the x.
Yeah, there you go. So it's going to be this one, isn't it? Right? So negative 3, 0. Jump. Okay? Make sense? Okay, what about these? Now let's talk about these. There's a lot of stuff like this on SBAC. These are really simple. There's a couple ways you can think about this. One thing I want to remind you of while we're talking about this, let's remind ourselves what there's only two ways we ever write linear equations, really. Ever. One of them is what? Robert, what's the most common way to write a linear equation? Probably y equals mx plus b, so slope-intercept, right? So if we can write it that way, mx plus b. So what's m? Some number. What's b? Some number, right? That's one way to do it. The other way to do it, we used a little bit, and we'll use it more in the future. This is standard form, right? ax plus by equals c, where a and b and c are just integers, right? Not fractions, they're just integers. So those are the two ways we could do this. So the question then is, can we write an equation in one of those two forms? If we can, it's a line. If we can't, it's not, right? So let's go through this list, and first of all, let's look at it this way, and then when we're done, we'll even think of maybe an easier way to think about it. It's even, but this is good review. So the first one, does the first one fit either of those?
Yes.
I don't think so.
Because
What's wrong with it?
As 1 over x.
Yeah, the x is on the bottom. Do you see any x's on the bottom in either of those?
No, sir.
We don't, right? The x's, what are the rules for the variables when we're writing a line? The variables are always on the top. They're never on the bottom of a fraction. Are they ever multiplied by other variables? No. They're always by themselves. What power are they to? First power, right? So this one doesn't work, and the problem area is right there. I have a 1 over x, so it's out. What about the second one?
Yes.
That's fine, right? I could easily put this one into this form, right? just by moving the y term to the other side. And then I'd have the x term and the y term on one side and a number on the other, right? But we can just see that, look, it passes the test. The variables are by themselves. They're not multiplied by other variables, and they're to the first power, right? So that one's good. Okay, what about this one? What's wrong with it?
Extra power.
Ah, we got a power of 2. No good. Okay, next one.
Yes.
Good. That one's actually in that form, isn't it? What about the next one?
Yes.
It is, because all I'd have to do is distribute the -6, and then I would have it in that form, wouldn't I? Right? But once again, the variables are not multiplied by other variables, and they're on the tops of the fractions to the first power. Okay, what about the bottom one?
No, it's a bit of squared.
Ah, okay, if I did distribute, I would end up with an x squared there, right? So that one's no good. So we get 3. Okay? If you have Desmos, how could you probably do this one really easily?
Just put them all in.
Graph them all and see which ones are lines. Okay. All right, what about this? So this takes us back to Unit 5 stuff. So this is good review. Given the function y equals 3x squared minus 12x plus 9. Okay, we want to know, place a point on the coordinate grid to show each x-intercept of the functions. We want to know where it's on the x-axis. Well, what happens on the x-axis? What's true for every point on the x-axis? Y equals 0, right? So think what we're doing here then. We're plugging in 0, for y, right? And that gives us the equation 3x squared minus 12x plus 9 equals 0, right? So that's just a quadratic equation in standard form, right? Now think about, there's so many different ways we've talked about this, and it sort of all comes together now. So yeah, y is equal to 0, that's the x-axis, but didn't we also recently say when we're talking about quadratics and polynomials that the real zeros of a function always correspond to x-intercepts, right? The imaginary zeros don't, but the real zeros always are x-intercepts, right? So all we have to do is solve that equation. Well, I could do it right now. I mean, what could I do right now without doing anything else? Look at that. It's a quadratic equation in standard form. That would be a great idea to divide by 3. And we'll do that. But what if I didn't even do that? I could get the answer out of this out. What can I always do with a quadratic equation in standard form? Quadratic formula. A is 3, B is negative 12, C is 9. Problem, I mean, that's going to work. It's inconvenient because I'm going to get big numbers in the formula because I could make them smaller, couldn't I? The suggestion is, Vincent suggested dividing by 3. Good idea. Right, if we divide both sides of this by 3, 0 divided by 3 is still 0. What about the other terms? So I'll just divide each term by 3. 3 over 3 cancels, so I get x squared. 12 over 3 is 4, and 9 over 3 is 3. So now I got a couple choices. I could use the quadratic formula now, and it'd be a lot easier because I've got smaller numbers. Is there another option? I mean, I could, but we won't even bother with that. Are there magic numbers here?
Yes.
There are. What are they?
4 and 1. Well,
No.
3 and 1.
Okay, careful.
-3 and negative.
Negative 3 and negative 1. They got to multiply to positive 3 and add to negative 4, right? So this breaks up into x minus 3 times x plus 1 equals 0. So what are my solutions? 3 and 0, right? If I set those equal to 0.
It would be negative.
Oh, sorry, that should be negative 1. So, I mean, not, did I say 3 and 0? 3 and 1. Duh. Okay. 3 and 1. Magic numbers were negative 3 and negative 1. Okay, so what's the time limit on SBAC? There's no time limit. So should I check?
Probably.
Yeah, for sure, I should check. It's easy to do. So if I plug these back into the original equation, I should get 0 for y, right? So let's try it. If I put 3 in up here, I'm going to get 3 times 9 is 27, minus 36 is negative 9, plus 9 is 0. It works. What about 1? 3 times 1 minus 12 times 1 is negative 9, plus they both work, right? So I get my x-intercepts. First thing they want me to do is plot those. So 1 and 3, okay? Now the second thing they want, it says place a point on the coordinate grid to show the minimum value of the function. Okay? So what about that? How am I going to do that? If I go back to my original, here's my function, right, that I'm trying to graph. We solved for the x-intercepts, but now they want us to find that's the vertex, isn't it? Right? So we've got the function y equals 3x squared minus 12x plus 9. Right? Now what can you tell me about that? What's the shape going to be? Parabola, it's quadratic. Does it open up or down? It opens up. Can anybody tell me, without doing any math, hardly, what the x-coordinate of the vertex is? 2. How'd you get it, Cheyenne? Go in the middle, right? Because we know it has to have symmetry, right? It has to have folding symmetry about the axis of symmetry, right? And so when I fold the paper, doesn't the vertex have to be on the fold in the paper, right? So we've done that a bunch. It's the average of the x-intercepts. So the average of 1 and 3 is 2, right? So we know that h equals 2. What else could we do? If we go back to, that's the best way to do it, because we already did the work to find the x-intercepts. But we do have a formula we could use also. If this is in standard form, right, ax squared plus bx plus c, does anybody remember what the formula is for finding h, which is the x-coordinate of the vertex? That's it, negative b over 2a. So that also gets it to us. That's going to give us positive 12 over 2 times 3. 12 over 6 is 2. Either way, right, we're going to get 2 out of it. How do I always find the y value for any function? Plug in the x value, right? So if I plug in 2 for both of those x's, that's going to give me the y value. That's fine. Yeah, go ahead. So that's going to give me y equals 3 times 2 squared minus 12 times 2 plus 9. So let's see. 3 times 4 is 12 minus 24 plus 9. So negative 12 plus 9, what's that? Negative 3. Okay, so then that tells me that the vertex is at 2, negative 3. So if we graph that, 2, negative 3 is right there. That's it, right? So the parabola opens up. Makes sense, doesn't it? Okay? All right. How could we obviously do this in Desmos? Type in the function, and then I just click on the 2 dots that are the x-intercepts, and then there's going to be a dot at the vertex because that's an important point. So I click on that one, it gives me all the coordinates, and I'm done. Okay? How about this one? This is something else that we've done. It's been a while, and you may not remember doing this, but I bet this will come back to you. So and make sure you read these. You know, these story problems like this, their research shows that most people, when they read story problems, they just give up. Don't do that, because people that write the test know that. They're not hard. They're just, they have words in them, right? Okay, the depth of a river changes after a heavy rainstorm. Its depth in feet is modeled as a function of time in hours. Consider the graph of the function. So that's just what the graph is telling us, isn't it? What's the y quantity on this one? Depth in feet. So y stands for the depth of the river in feet. What's the x quantity? Time in hours. Okay, so this is depth versus time. So it says enter the average rate of change for the depth of the river measured as feet per hour. So right, we're trying to measure this in terms of feet per hour between hour 9 and hour 18. So what can you tell me about hour 9 on the graph? Okay, so when x is 9 hours, y is 18 feet, right? So there's an ordered pair, 9, 18. What can you tell me about hour 18? Okay, depth is 21 feet. So there's 18, 21. So now here's the key part of this. What is an average rate of change in terms of those 2 points? Average, what's a rate sound like? What's rate always been in math?
Ratio.
It's been a ratio. Hasn't it always been a slope, right? When you talk about a linear equation, hasn't it always been, if you think about the equation of a line, y equals mx plus b, in every story problem you've ever done, hasn't this been the rate, and hasn't that been the start value, right? So when we're talking about an average rate of change, we're just talking about a slope, aren't we? Well, what slope are we talking about with those 2 points? Yeah, the one through the 2 points. We're just going to draw a line through the 2 points, and we did this way back at the beginning of the year. I mean, months and months and months ago, right? We just made a slope triangle out of this, and the slope is equal to the rate, isn't it? So let's make our slope triangle, and what do we get? What's the rise going to be here? Now, you got to be careful. Read the graph carefully. Plus 3, right? So it's going to be plus 3 feet. Right? Everybody agree that's the rise?
Yeah,
What's the run? What is it again? 9 hours, okay. So then if we just use rise over run, what are we going to get? So we get 3 feet over 9 hours. Well, then we just turn this into 2 parts, right? We'll just turn it into the number part. What is 3 over 9 reduced to? 1/3. And then the units are just feet per hour, right? So it's changing at an average of 1/3 of a foot per hour, so 4 inches per hour. But they just want it in feet per hour, so that's our answer. Okay? All right. Okay, here's something very simple, but we haven't really done this year. So easy, though. You've done this before in Algebra 1. You've done stuff like this. It's no big deal. When you have a ratio, right, so we have 2 fractions set equal to each other, what did you guys do back in Algebra 1 when you want to solve a ratio? What did you always do? Yeah, so if you're solving a ratio, so if I've got 2 fractions set equal to each other, what did we do? And the whole goal here is the fraction, we want to get rid of the fractions. So what did we do to write this as an equation without fractions? We cross multiplied, right? Okay, I know you're all thinking it. You're too shy to say it, but we just cross multiplied. So let's look at what this means then. If we're going to cross multiply, there's one cross product. The x minus 4 times x, right? So x times x minus 4 equals the other cross product, which is what? 3 times 7, which is 21. And then from there, now we can deal with that, right? Now this looks familiar. Now what would you do from here? Distribute. Okay, so we distribute the x and we get x squared minus 4x equals 21. Now what would you do? Yeah, you got to set it equal to 0, right? This is going to be a quadratic equation. We've got to put it in standard form. So we put everything on the side where the x squared is positive. So x squared minus 4x minus 21 equals 0. And now it's just a quadratic equation in standard form. So you got all kinds of strategies for that. So let's go through the solution up here that the student did, and let's see if we can find any mistakes. So first part's fine, right? They did the blue cross product, x times x minus 4. Next step, they multiplied the 3 by the 7. So far, so good, right? Then they distributed, and they got the same thing we did. 21 equals x squared minus 4x. They subtracted the 21, just like we did. And then they were smart. They picked magic numbers. Are those correct magic numbers?
Yes.
They are. Negative 7 times 3 is negative 21. They add to negative 4. They found the zeros, positive 7 and negative 3. Are there any mistakes?
No.
It's fine. How could we check it, though? To make sure, plug them in. So if we want to really make sure, we would just plug in negative 3. If I plug in negative 3 up there, what am I going to get? 3 over what's negative 3 minus 4? Is that equal to negative 3 over 7? Yeah. Both of those, positive divided by negative just means a negative fraction. So those are equal, right? What about positive 7? If I put 7 in, I'm going to get 3 over 7 minus 4 is 3, right? So is 3 over 3 equal to 7 over 7?
Yeah.
Yeah, they both work, okay? Okay, last, is probably as far as we'll get. But it's a good one to end on. Okay, so what about this one now? This is something, once again, this is maybe slightly new, but not very much. Not very much at all. We've talked about all the ingredients for understanding this throughout the year. We've said for a long time, you've said it in other classes too, but we've said it more this year. What are the 2 rules for real numbers? We can think about the 2 things we can't do for real numbers. So you can't have i's. You can't take a square root of a negative number, or it's not going to be real. You're going to get i's. Okay, so there's one that we've done a lot with. The other one's even more basic. You can't divide by 0 ever, right? Dividing by 0 doesn't work. Dividing by 0 means you get infinity, which is not a number. Okay. So on these aren't ones that deal with square roots, but they're ones that deal with dividing by 0. So when they ask this, it says choose the domain for which each function is defined, right? So in other words, what are the x values that we're allowed to plug in? There are some places where these functions are undefined, meaning those x values are not allowed, okay? I can't pick any x value in these cases that's ever going to cause me to divide by 0, because some of these are fractions. So like in this first one, for example, what's the x value that would make this one blow up? Because I can't divide by 0. So what's the x value that would force me to have a 0 in the denominator? 0, right? How do I find that? There's a really easy way to do it. All you do, if you've got a fraction and there's a variable in the bottom, all you have to do is take whatever's in the bottom and just set it equal to 0 and solve. And those are the values you can't have, because you can't have anything that equals 0 on the bottom, right? Okay, we'll finish that up tomorrow. Whew, a lot of stuff.